So, welcome to question B. So, we have a curve which is smooth at this point, no vertical tangent line. This means that f differentiated with respect to x at p1 is non-vanishing. Right. And explicit functions then defined in a neighborhood of this is implicit function theorem. The linear terms gives the tangent line. Now subtract the linear term and get the higher order series. Boom. Right. Then we choose a point on the tangent. All right, so we have to show that the order of tangency equals the lowest power of p occurring here. Oh my. So what do we do here? I think we should first translate so that the point is in the center. And next we should rotate or make some linear change of coordinates. So that the tangent line is horizontal. The point of that is to make this formula very simple. So, well, we have to make implicit differentiation. So let's do that. So fx oh, now inserting the point gives this vanishes. This one equals 0. So this equals 0 as well. So we differentiate once again. Oh, well, we'll just write it here. This, I'll just make it blue. This guy vanishes. This guy vanishes. This guy vanishes. So insertion gives that this we should call something. We call it A. Oh, that's A. Oh, that's not, that's not, that's not. Now it's pretty clear that that as far as the derivative with respect to x vanishes, we will get a term, an equation like this. That's the center, 0.0. And minus 1 times. Right. So it's the order of tangency m equals what is it called? Well, that's distinct from 0. So that was the first part, I hope. The next part is to compute this guy. And our point, to compute this guy. The point here is the center, and this lies on the x-axis. So it may either be on infinity 0, 1.0.0, or it may be 1.0.0. So that's the two cases we have to compute. I think we'll have to write up the expression for f, an explicit expression for f. What could it look like when we have this, for instance, for m equals 3 or m equals 2 or m equals 4? Now, what do we have? Well, let's write it up and then see what we can conclude. So first, the center gives naught. So a naught naught vanishes, and differentiation with respect to, let's just do it explicitly. Etc. So now, what did we have here? The derivative with respect to x vanishes, and the derivative with respect to y does not. So when we derive with respect to x, this disappears. This gives it, oh, let's just write it. Let's write it. So this is the only guy that comes out. All these will vanish. Differentiating with respect to y gives a naught 1. Oh, a picture begins to make itself visible. So f differentiated, actually many things don't matter at all. We're only interested in f differentiated with respect to x many times. So fxx, that only contributes from, now I kind of missed number 2 here, so that explains some confusion. We'll just correct it to number 2. So I got a little ahead of myself there. Why doesn't it work? I'll just use the normal mouse here. So it has gone out, so we'll have to stop the video and then take it up in a while. So there we are back again, and I hope I can edit it now. Now it's working. So obvious, oops, f differentiated n times with respect to x All right, so perhaps we can have it up here. F tilde equals where n is the order of the polynomial. And we have to compute f of, and if we go back, the tangent line was x line, so let's say it's 1, 0, 0, the point at infinity. Let's do that first. So that's just tx point 0, point 0. So that means that all terms where y occurs will vanish. And since we put z equal to 0, then only the highest order. So that means we are not quite sure what this will give. I'll try once again. We have all of these vanishing up until m. So lowest order yeah. Oh, lowest order term. Lowest order term is this one. All right. And then if we have a point where z equals 1, that's an affine point. All the points with y, chick, 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 will vanish. So we are left with this as well. How nice. And now we have to put t in there. So if order is m, no, that's not the order. If the order is n, then the first term that will have what I'm doing this is wrong. I don't have an x there. We go back here. So x's, y's, and z's are numbers. So no variables occur. So this was naught. So it's a number times t, a number times y. And if z2 is unity, then it's just t and t here. If x, so x may be any number there. Actually, we could have made x2 any numbers. So that would have solved it perhaps in one go. So this x is just taken away, and this x, there we go. So this one has z to n minus 2. So it'll always be t to nth. To the order of the polynomial. Now, what did we have to prove? So it should hold for any point, any projective point on the tangent line. So it may be affine or at infinity. And if it's affine, we do have a 1 here. Oh, and we have a 1 here. That's unity as well. No, because, oh yeah, it's x point, y point, 1. X point, y point, 1. That means that we have to have t point 0.1. So now it's down again. Maybe another one will work. Yes, it did. And this should be 1 plus t. In case both points are affine. Ah, so that actually solves the problem. Because when we have some powers of z up until the highest order power n, and that is z equal to unity, and here z is z equal to 1 point t, so that means that these are wrong. So here we have, here from the first t we get t, so that was too little. T to m, and then 1 plus t times n minus m, and t to m plus 1 times 1 plus t to t minus, provided this is greater than or equal to 0. And when we expand this, we get a m naught t to the mth plus higher order terms. Whoa! That solved point B, problem B. Surprisingly difficult, I should say. Now, show that m does not change if you make a linear change of variables. Yeah. So, how can that be a problem? Because isn't this invariant with respect to linear changes of variables? I think that's extremely obvious, that the lowest power occurring is independent of any linear transform of the points. I don't see the problem. Honestly, I don't. Well, if I'm missing anything here, then I haven't solved it. But let's believe that it simply follows from the invariance of this term with respect to linear transformations. So that was that.